We're going to look at tools for protein structure, search, and alignment. We'll show how to read your in-house structures or structures from the PDB, and then take those structures and search the PDB by sequence similarity, ligand substructure, and 3D structure similarity, as well as Pharmacophore similarity. So you can search by the pocket to find similar folds, or by pocket and search for similar pharmacophoric properties in the pocket. Show you how to retrieve the relevant literature structures, and then how to align and superimpose those structures. So we're going to start by searching by sequence and ligand chemistry. So we have the tools here. We're going to use, as an example, PDB1XBB, which has Gleevec bound to it. We're going to go to ICM to look at that now. So we can search by sequence from the PDB, either the atom records in the PDB, or by the SecRes records, or by UniProt sequence. So if you want to read in your in-house structures, you go to File, Open, and then locate the PDB structure. Just for this example, I'm going to read a PDB directly from the PDB website, from using the PDB search here. We have 1XBB. So if we want to find other structures in the PDB, or we can do that by sequence. So we right-click on the A chain, which is the protein chain. We choose UniProt and Construct, and choose Read, so Extract, Construct, and UniProt. And then we can choose to read the 3D-seq information from the PDB. You can read the 3D-seq and the Construct and the UniProt. As just an example, I'm going to use this. We're going to trim it to the N or C terminal and go OK. It gives us the alignment. And it gives us the, you can see that the ResSeq sequence is here. The PDB sequence from the atom records is here. We can see we have a gap in the chains here and here. But if you want to find other structures with similar sequence, we go to right-click on the sequence. We could use the SecRes sequence here and search PDB by homology. A number of clicks. There's the p-value, and then you could choose protein, and you could also search nucleotides, but we're obviously going to search protein, and we can just go OK. And this gives us the a table with the sequence identity, and in the second column we have the PDB code for each of those, each of the hits. So obviously we could increase the number of hits if we wanted to, but we just load these by double-clicking here. And you can see this one isn't actually in the same coordinate frame, so we need to superimpose them. So to superimpose the structures, we show the A chain of 1. It's going to make this table a little bit smaller. This is the A chain of the one I just read in by double-clicking, and the original 1XBB. We just select using command. Go and a command tool, a command button on a Mac, or Control on Windows or Linux, and then go to Display tab, and then we have the Superimpose button here, and you can superimpose. Now the binding site is superimposed, and you can also superimpose multiple structures just by selecting them and using that superimpose button. There are other tools for superimpose here, which you can be more specific about what you're trying to superimpose, but this works fine. You may also want to search the PDB by chemistry. So to do that, we right-click on the ligand and choose Edit. can just edit compound. We could search, we could just select the whole ligand and search by that, or we could maybe select, just delete this part, and if we delete this part, and then we can just leave this phenyl amine pyrimidine group, and we can search. If I just delete this, we can search using this substructure. So you just copy it, and you can go to edit, copy, or Control C, and then we go to the search tab here, the PDB search, and we have a ring here with a pencil. It opens the editor again. And you can just paste it here, and then close, and you see the smiles and smarts. You can have smarts here to do the search, and you just click on the binoculars button, and then you get all the structures from the PDB that have this search string that we were looking for. So they mainly find Gleevec again, but there's some other further down that are a bit different modifications. You can load them just by double clicking and displaying the structure. Just want to show you some other ways to search. You can also search by fold. So you read in your protein structure, you select the pocket or some region of the structure. It doesn't have to be contiguous. It could be a non-contiguous selection, for example, a binding pocket. And the method performs a fast 3D similarity search on the backbone stripped version of the PDB using distance RMSD between C alpha atom distance matrices. And then once it's finished, you get a table with the top matches and the RMSD. So practically in ICM to do this, we go to ICM, we read in that 1 XBB. You could make a selection around the binding pocket. So around this ligand, this is the Gleevec bound. So you right click, choose neighbors, 5 angstroms, and then we'll look for pockets that have similar structure, or you could just right click and drag in this region and look for other folds in the PDB that are similar to this. You go to Tools and choose 3D Similarity PDB Search, and it takes a couple of minutes to run. Let's go to that menu so you can see the options. You choose an RMSD threshold, so if you want to find more distantly related structures, you can increase this a bit. It takes a couple of minutes to run. You can parallelize the job to speed it up. And when it's finished, you get a table like this. So we have the entry and the RMSD compared. So we obviously find 1 XBB. I just double click, and in this case, they automatically superimpose. So that's going to, so you can see them. One entry. Double click and load them. Let's find a bigger one that has a bigger distance. And yes, they're automatically superimposed. And this one has an additional chain, so it's down here, but the main structure is here. Yeah, so you can rank them, you can read them in, and search by 3D structure. You may also want to search by the pharmacophoric property of a pocket. So rather than search by sequence or structure or 3D structure, you're searching by the actual properties of the binding pocket. So this is a ligand binding site superposition and comparison method described by Max Totchoff, who's our Chief Technology Officer here at Molsoft. Originally, it was developed for small molecules, so you can superimpose small molecules based on these 7 pharmacophoric property fields. but it has utility for ligand binding site superposition. The paper introduces an algorithm that uses optimal superposition of the continuous pharmacophoric property distributions to identify distant homologs and convergent binding sites with good quality superposition observed. So the method uses APF, and it's pretty sensitive and accurate. It aids drug design and functional annotation, and it's also good for like finding off-target screening as well. So if you have a distantly related protein that may have similar properties in the pocket, so it may bind similar ligands, even though it may not have similar sequence to your target. And just to run this practically in ICM, you just this is similar to the 3D fold. You just right-click and make a selection around the pocket. Neighbors here. In this case, we would just want one structure. We're just going to use one XBB. Because we're using pharmacophoric properties, we need to convert this to an ICM object. So we right-click and choose Convert. You can watch other videos about these options, but we're just going to optimize hydrogens, and we're going to optimize histidine, tautomers, and asparagines and glutamies and other things. Make it to an ICM object. And then we right-click on the ligand, choose neighbors. You could use whatever radius you want. I use 5 angstroms. Go to Tools, and then the option is here called Scan Pockets. You need to download the pocket database. So you click here and you can download it. And you run, and you get a similar table to the structure where you have the you can just double click, you have the entry PDB code, and double click and load it into ICM. And the pockets will be superimposed on each other. Okay, thank you.